Hey ladies and gents, I'm going to demo how to do section 4.3 number 44 just to give you a second look at that type of problem, and then I'm going to go over the review question number 100 primarily because of the idea of bearings, and being able to draw a picture with that type of information is sometimes a challenge if you've never had any exposure to bearings before. So let me start with number 44. We're going to find the cosine of theta, and we are going to find the cotangent of theta, given that the sine of theta is equal to 1 over 4. And we also know that tangent of theta has to be negative or less than 0. Now, the first thing I'm going to note is that the tangent of theta has to be negative, and we know that tangents, which are sine over cosine or y over x, is going to be positive here and negative here and here. So the only quadrants we are interested in for this problem, number 44, because of this constraint, is here or here. So we're down to a 50-50 location. The reference triangle is either going to be in the second or fourth quadrant. Now, we're going to look at the sine. The sine of theta is equal to 1/4. That is a positive value. So again, I think to myself, okay, where is sine positive? Sine is associated with the y coordinate. Y coordinates are positive here and here, negative here and here. So it's positive value, so it's going to make sense here or here. Now, the only place that both of them are happy or true or an overlap is happening is here and here. So I am going to create a reference triangle in that second quadrant just because of that information. So I know that I'm referring to this quadrant right here. I know the sine is opposite over hypotenuse. So this triangle, here's my reference angle right in there. The opposite side is 1, the hypotenuse is 4, and if I use Pythagorean theorem, I'll end up with the square root of 15. But because you are going this direction on the x-axis, this direction, we are going to have a negative square root of 15. So now we have all three sides of our triangle. Life is good. So I'm just going to say cosine of theta is equal to the adjacent side over the hypotenuse. And then cotangent of theta is equal to the, not the opposite over adjacent, but the adjacent over opposite, which is 1, so I'll just leave it like that. Okay, so that's a quick look again at how I know that I'm working with my reference triangle in the second quadrant. Okay, on to number 100 on the review. This is kind of an interesting problem. It talks about finding distance and bearings. Let me just start with what a bearing is. A bearing is always coming off of the true north, and if you think about, actually I can do better than this lemon. We know that north is up here, and bearings are always coming off of the north clockwise. So if for some reason it says 90 degrees, the bearing is 90 degrees, we know that we're starting from the north and we're going to end right here with a 90-degree angle. In the actual problem, it says you have a bearing of 115 degrees, which would be a little bigger than 90 degrees, and also a 123-degree angle. So these are all coming off the north. It all comes off the north. So this is totally different than when you're dealing with right triangle trigonometry, unit circle, because we go counterclockwise. Bearing, which is dealing with really everything but math. Well, I don't know. It's just kind of how it is. It's kind of like when we were talking about the latitude and longitude, but everyone knows the bearing comes off the north. And if you've never heard of it before, that's okay, because that's why I'm teaching you it. Okay, so we have a shore here, and this is the shore of the land over here. I'll say shore. And we have 2 points on that shore, here and here. And it says that shore, so I'm again reading number 100 here. It says the bearings of 2 points on the shore from a boat are 115 and 123 degrees. Assume the 2 points are 855. So this right here in here is 855 feet apart. How far is the boat from the nearest point on shore if the shore is straight and runs north to south? So this is north, here's south, the shore, all that kind of good stuff. So if we're talking about a boat that has both bearings at over 90 degrees, the boat's going to have to be down here. So here's my sailboat, and I'm going to draw myself a triangle. And this is not that accurate of a depiction, but it's decent. And I'm going to say that this one, this bearing, is going to be the bigger of the two, because if you just look at the angles themselves, it's bigger. But it's 123 degrees, where this one, which isn't nearly as big in here, is 115 degrees. So the main question, though, and this is what you need to really understand what they're saying here, is that we really want to know the length from the sailboat to the land at its closest. So it's not saying one of these 2 points that are already that we're using as a bearing, but this length right here, this orange line, that's eventually the length we want to know, and we'll call that x. Now, you can set up very much like we did in class a system of 2 trig equations and solve those, or you can use your law of sines like we talked about. Either way is just fine. And because we kind of focused on more of the system, I think this problem I'm going to show you more, or kind of remind you again how to use your law of sines. And it's easier, to be honest. Okay, so if we know that this in here, this purple triangle is 115 degrees in the one angle, I know that this angle right in here, there's lots of arrows here, this angle right in here, if I go 180 minus that 123, we're going to have a 57 degree angle in there, which then also you can then figure out that this then is going to be your 8 degree triangle. So, and I'm going to, just because it's, the picture could be better, but anyway, we have a 855 foot length over, I should say feet, over sine of 8 degrees, and of course you can go sine of 8 degrees over 855 feet, equals, now I can't find x right away, I'm going to find this variable, let's call it y, that length, y over sine of 57 degrees. So you can find, using the law of sines, your 2 other sides of this non-right triangle, but the only one that I'm going to be really interested in is that y length, because then that's the hypotenuse of my right triangle down there that includes that orange line segment, or the length that we want. When you cross multiply and solve this thing, you end up with y is equal to, I can't remember what it is, so I'm going to have to calculate it really quick, so bear with me, times 855 divided by, and I assume you're doing this as well, so it's going to take you a minute. I have 5,152.3127 feet. So that length y is 5,152.3127 feet. Now, that's all great, but now we need to know the length of the closest spot to the shore, that orange length. So I'm going to draw that solid triangle right down here so we can kind of get it all cleaned up here. I know that this is x, that's what I'm trying to find. I know this is a 90 degree angle. I know that, let's see, because I know that angle up there is 115 degrees, so I know this in here is 65 degrees. And what else do we know? Oh, we just found this hypotenuse, which is 5,152.3127. And you know what? At this point I could stop because I have no doubt you can figure this out. But since I'm on a roll, I have, let's see, sine of 65 degrees is equal to the opposite side over the hypotenuse. When you solve for x, you will end up with that answer of 4,670 feet, and you will be amazing. So, the picture is worth 1,000 words here, right? So bearing comes off of your true north, rotates clockwise, something new for maybe many of you if you're not haven't had a physics class, or haven't had an engineering class, or haven't had anything to do with sailing or boating or geography in general. So it's good to know. And we talk lots about bearing here in the next chapter, so it's a good intro. Okay, so if you have any questions, come on in the morning. Otherwise, I think that would hopefully help you with that problem. Take care.